Hello, this podcast is about the basic characteristics of vectors. We're going to be looking at and comparing vector and scalar quantities. We're going to be looking at coordinate systems as they apply to vectors. We're going to be looking at some of the basic math properties of vectors. We'll see how to graphically add and subtract vectors. And lastly, and most importantly, we're going to look at unit vector notation and see how powerful that is in allowing us to quickly add complex vector combinations. First, let's talk about vector quantities and scalar quantities. Vector quantities, they have magnitude and direction. Scalar quantities have magnitude but no direction. So here's some examples of vector quantities: position, velocity, force, torque, displacement, acceleration, momentum. These are the common vectors we'll be studying in mechanics. Notice that the direction matters. For instance, the magnitude of displacement, let's say we moved 5 meters, but it makes a difference whether we're moving 5 meters to the right or 5 meters to the left. Similarly, if we push on something with a force of 100 newtons, it's certainly going to make a difference whether we push up on the object or push down on the object with that force. Now, let's look at scalar quantities. These have magnitude but no direction. Time, speed, energy, mass, distance, weight, work. Oops, got time in there a second time. Well, these are the scalar quantities we're going to be working with in mechanics. Notice, it doesn't make sense to talk about a direction. If we have time, you can't have time to the right or time to the left. Energy, you can't have energy up or energy down. Same thing with mass. Is it 100 kilograms to the left or 100 kilograms to the right? Just doesn't make any sense. So these are scalar quantities. Now that we understand that, let's take a look at some coordinate systems. And of course, we're most familiar with the Cartesian coordinate system, also known as the XY coordinate system. We learned this early on in our math classes, and we use it frequently. We have the horizontal axis, which is known as the x-axis, and we have the vertical axis perpendicular to the x-axis, and this is known as the y-axis. And this coordinate system expresses the location of a point from the origin as a horizontal and vertical distance. So for instance, if this coordinate was 2, 3, then the point would be 2 units to the right of the origin on the x-axis and 3 units up from the origin on the y-axis, and that would give us our point. Polar coordinate systems, something that we don't learn about in most math classes. In fact, I don't believe you're introduced to it until you take Calculus BC. Here we have an origin, just like we did with the Cartesian system, but now instead of an x and y axis, we express the location of a point by an angle of rotation and a radius. So notice in this coordinate system, instead of it being the point being labeled xy, it's labeled r theta, where r is the distance from the origin and theta is the angle of that line or radius. And theta is measured from the fixed axis in a counterclockwise direction. So let's summarize what these coordinates mean. In the Cartesian system, the x is the horizontal distance between the point and the origin, and y is the vertical distance between the point and the origin. Now, in the polar coordinate system, r is the distance between the point and the origin, and theta is the angle between r and the fixed axis, which in this case resembles the positive x-axis. Now let's look at how we can go between the two coordinate systems. We can use right triangle geometry and our trig functions to convert between the two systems. So if we have an xy coordinate, we can convert it into an r theta coordinate or vice versa. So let's assume first that we have polar coordinates of r and theta. We can use our cosine and sine functions to come up with the y and x coordinate. The x coordinate would be arrived at by taking r times the cosine of theta, and that will give you this distance, which we know is the x coordinate. And similarly, we can take r times the sine of theta, and that will give you this distance, or this distance, which is the y coordinate. Now, to reverse the process, if we know the x and y coordinates in the Cartesian system, we can come up with the value of r by using the Pythagorean theorem. So x squared plus y squared, the square root of that sum will give us the length of this hypotenuse, and of course that hypotenuse is just the distance between the origin and the point. And we can find this angle theta by taking the inverse tangent of y divided by x. Let's look at some important properties of the vectors. Vector A is equal to vector B if they have the same magnitude and point in the same direction. Negative A has the same magnitude as A, but points in the opposite direction so that A plus negative A equals 0. A plus B is equal to B plus A. The order in which you add the vectors doesn't matter. However, when you're doing subtraction, order does matter. A minus B is equal to A plus negative B. A minus B is not equal to B minus A. Finally, let's take a look at scalar multiplication. That's where we're taking a scalar number and multiplying it by a vector quantity. And in this case, the vector has the same direction as the original vector, but its magnitude is the factor m of the original magnitude. So for instance, if we start with vector A and we multiply it by 1/2, the direction of the vector is exactly the same, but the magnitude is going to be half of the original vector. And that's represented by this length of the arrow being half the original length. Similarly, if we multiply vector A by 2, once again the direction is the same, but the magnitude is doubled, and we represent that by the length of the arrow doubling. Now let's talk about how we add vectors graphically. So there's two ways of doing this, and they'll yield us the same results. There's the triangle method, which is also known as the tail to head method, and the parallelogram method. So let's look at some examples. First, let's take vector A and vector B, and we're going to add them. So we can do that in the triangle or tail to head method by taking the first vector, then we take the second vector, and notice we place the tail of the second vector on the head of the first vector. And then our resulting vector A plus B starts at the tail of the first vector and ends at the head of the second vector. Notice if we reverse the order of addition and do B plus A, we still get the same vector, but we start with B, and then we take the tail of A and put it on the head of B, and our resultant vector B plus A starts at the origin of, starts at the tail of vector B and ends at the head of vector A. Now there's another way of doing this. If we have our vectors A and B and we want to add them together, we can create a parallelogram. Place the tails of vector A and vector B at the same point, then go to the head of vector A and draw a dashed line parallel to vector B. And you repeat the process then. You go over to vector B and you start at the head of vector B and draw a dotted line, a dashed line parallel to vector A. And where these two dashed lines intersect, that will be the head of your resultant vector, a plus b. Let's take a look at vector subtraction. We're going to take the same two vectors that we had in the first problem, only we're going to subtract a from b. Now remember back in properties that negative b is the same vector as b except it points in the opposite direction. So instead of adding a plus b, we're adding a plus negative b because that's the same as a minus b. So in our in our triangle method or tail to head method, we're going to take the tail of negative b and place it on the head of a, and then our resultant vector starts at the tail of a and ends at the head of negative b. Now, if we go ahead and do b minus a, we'll do the same thing, only now we're adding vector b to negative a. And so notice negative a is in the opposite direction of our original vector a. And if we do the tail to head method again, we see that we get a resultant vector b minus a that is different than a minus b. So it does matter what order you subtract these vectors in. Now, the parallelogram method, we just use the same process. We have to remember that when we're subtracting b from a, it's the same as adding negative b to a. So we go ahead and place our vectors at the same origin, and we draw our dashed lines parallel to the other vector, and our resultant vector starts at the origin and ends where the dashed lines intersect. And once again, you can see that we get the same resulting vectors using the parallelogram method as using the triangle method. So let's learn about unit vectors. And again, what we've covered so far has been basic review and is really a setup for unit vectors. First, let's start with some definitions. We have component vectors. These are defined as two or three mutually perpendicular vectors with magnitude a sub x, a sub y, and a sub z that when added together equal an overall vector. Unit vectors, these are vectors with a magnitude of 1 that point in the positive x direction. We designate that as the I unit vector. Positive y direction, we designate that as the j unit vector, and the positive z direction, that would be the direction coming out of the screen, and we designate that as the k unit vector. And we have the resultant vector, and that's the overall vector, sometimes referred to as the total vector, that can be represented by two or three mutually perpendicular vectors. So again, the component vectors are the perpendicular parts of a total vector, also known as a resultant vector. And unit vectors are similar to component vectors except they have a unit with a magnitude of 1. So for instance, the I unit vector is going to lie on the x direction, at x-axis, and point in the positive x direction and have a magnitude of 1 unit. The j unit vector is going to point up from the origin on the y-axis with a magnitude of 1 unit, and the k unit vector is going to point towards us coming out of the screen on the z-axis and have a magnitude of 1 unit. Now, polar coordinates, if we go back to our coordinate systems, polar coordinates best represent a resultant vector because the coordinate r gives us the magnitude of the resultant or total vector, and theta gives us the direction of this total vector. Now, Cartesian coordinates are best to represent component vectors, and that's because the x-coordinate tells us the magnitude of the x component, and the y coordinate tells us the magnitude of the y component. And the plus and minus signs tell us the direction of the components. Positive is to the right on the x-axis and up on the y-axis. Negative is to the left on the x-axis and down on the y-axis. The power or utility in unit vector notation is that it allows us to represent a resultant vector in Cartesian coordinates instead of polar coordinates. In unit notation, vector A is equal to a sub x, which is the magnitude of the x component, times the unit vector I, remember that's the unit vector that lies in the positive x-axis, plus a sub y, which is the magnitude of the y component, multiplied by the unit vector j, and that's the unit vector that lies in the positive y direction. Another way of stating that using the coordinate systems is that the r coordinate is equal to the x coordinate from the Cartesian system times the unit vector I plus the y coordinate from the Cartesian coordinate system times the unit vector j. So let's talk about computational methods. So if vector A is equal to a magnitude a sub x times the I unit vector plus a sub y, another magnitude, times the j unit vector, and B is equal to b sub x times I plus b sub y times j, then adding the two vectors a plus b can be written in unit vector notation as adding the x component magnitudes of the two vectors a sub x plus b sub x and multiplying that sum by I, the unit vector I, plus the magnitudes of the y components a sub y plus b sub y, that sum multiplied by the unit vector j. And now we can use the Pythagorean theorem to find the magnitude of this overall or resultant vector. And we take the sum of ax plus bx, we square that. We take the sum of a sub y plus b sub y, we square that, and then we add those two squares together and take the square root of that sum, and that'll give us the magnitude. Similarly, we can find the direction of this resultant vector by using the inverse tangent function. And in our numerator, we'll have the ay plus by, and we'll divide it by ax plus bx. And that inverse tangent will give us theta, the directional angle of the resultant vector. If we're doing subtraction, it's a similar process, only now instead of adding a sub x and b sub x, we're subtracting b sub x from a sub x, and we're subtracting b sub y from a sub y, still multiplying those quantities by their respective unit vectors I and j. And keep in mind, if we have a negative coefficient for a unit vector, that just means that it's pointing in the negative direction. And we can use the Pythagorean theorem once again to get the magnitude of this resultant vector, a minus b, and we can use the inverse tangent function to get the directional angle theta for that resultant vector. And finally, if we're doing scalar multiplication, for instance, suppose we're taking 2a plus 3b. What's the resulting vector from that? Well, we simply do the math to the individual magnitudes of the unit vectors. So 2 times ax plus 3 times bx. That sum will give us the coefficient for the I unit vector. And similarly, we're going to take 2 times a sub y plus 3 times b sub y, and that will give us the coefficient for the j unit vector. And once again, we'll use the Pythagorean theorem to find the magnitude of this resulting vector, and we'll use the inverse tangent function to find the directional angle theta for the resulting vector from the operation 2a plus 3b. Now let's move on and look at a specific example. So a bird flies from tree A to tree B and from tree B to tree C, and finally from C flies on to tree D. Its flight between the 4 trees can be represented by 3 displacement vectors. Vector A to B is 4.0i plus 2.0j. The m here stands for meters. That's typically how we place the units on the outside. B to C vector is negative 1.0. That means it's moving in the negative x direction, plus 5.0 times j. And again, the units are meters. And the third vector, C to D, is 1.0i plus negative 3.0j. That means it's moving in the negative y direction, or moving down. So these are the 3 vectors written in unit notation. And the question asks us, what is the bird's displacement after the 3 legs of its flight? Well, we need to add these 3 vectors. The displacement vector, the total displacement, A to D, is equal to the A to B plus B to C plus C to D vector. Now this will show you how easy this is to solve using unit vector notation. So for the I, to find out the coefficient of the I unit vector, we simply take all the coefficients, the I coefficients from the 3 individual vectors, and we add them together. Now of course the quantity here was a negative quantity, so we're adding a negative number. And we do the same thing for the individual j coefficients from these 3 individual vectors. And then we add them up, and that gives us A to D, this resultant vector in unit vector notation is 4.0i plus 4.0j meters. And now if we were asked to find the magnitude and direction of that, again, this is the vector in unit vector notation, but if we were asked to find the magnitude and direction, we would simply use the Pythagorean theorem to find the magnitude, and the magnitude of that total displacement would have been 5.7 meters, and the direction of that displacement would have been 45 degrees. So this shows you the power of using unit vectors when you're multiplying or adding several vectors together. And it's much faster than using the graphical method. So we've learned a lot about the basic characteristics of vectors. I hope this podcast has been helpful.